Dear learners, we will find the electric field created by different charged objects. First, we take a spherical shell, the green colored hollow sphere. It has a radius capital R and its center at O. It carries a charge Q. The charges are uniformly distributed over the spherical surface. So the electric lines of force are emerging normally from the spherical surface. We are to find the electric field at a point P at a distance r from the center of the spherical shell. As the electric lines of forces are emerging radially, the electric field at P, it is also radial, that is, it will act along OP as shown in figure. You look at the figure, this is the direction of E. We draw a sphere of radius r with center at O. Then this spherical surface is called Gaussian surface. It will then include P, as P is at a distance r from the center. We then imagine a small area, differential area at P. The normal to this differential area is along the electric field. It is also normal to the surface. That is, the direction of E and ds is the same. The electric flux of the differential surface d phi E equal to E dot ds, that is E ds cos 0 degree, which is 1, so E ds. The total electric flux of the Gaussian surface phi E equal to closed surface integration of the Gaussian surface E dot ds, that is integration E ds. The magnitude of E everywhere on the surface is the same, so it is a constant. It will come out from the integral E integration ds. Integration ds is 4 pi r square, so E into 4 pi r square, this is the total electric flux of the Gaussian surface. According to Gauss's law, epsilon naught phi E equal to charge Q, that is epsilon naught E 4 pi r square equal to Q. Therefore, E equal to 1 by 4 pi epsilon naught Q by r square. On the surface of the spherical shell, small r equal to capital R, so electric field is there, E equal to 1 upon 4 pi epsilon naught Q by capital R square. If we want to calculate the electric field inside the spherical shell, then P, the point P will be here inside the spherical shell and total flux, calculation of total flux is the same. Then total flux epsilon naught 4 pi r square E equal to quantity of charge enclosed in the Gaussian surface. This Gaussian surface does not enclose any charge, therefore it is 0, and therefore E equal to 0. The second charged object is a conducting solid sphere. The conducting sphere carries a charge Q. These charges move to the surface. All the charges move to the surface due to their mutual repulsions. A spherical charge distribution, a spherical surface distribution of charges is created like a charged shell, hollow charged sphere. Therefore, the calculation of electric flux and the results are the same as in a spherical shell. That is, the electric field outside the sphere E equal to 1 upon 4 pi epsilon naught Q by R square. The electric field on the surface of the spherical shell, solid sphere E equal to 1 by 4 pi epsilon naught Q by capital R square, and inside the solid conducting sphere E equal to 0. It is the same as in spherical shell. The diagram is also exactly the same. The green color indicates the conducting solid sphere. The third object is a non-conducting solid sphere. In case of a non-conducting solid sphere, the charges are distributed over the volume of the solid sphere. The calculation of the electric flux and the results for outside the sphere are the same as we have seen earlier. But for a point inside the sphere, the total charge inside the Gaussian surface is not 0, unlike the previous events. The total electric flux phi E into epsilon naught equal to charge within the Gaussian surface. Q divided by 4 by 3 R capital R cube, where R is the radius of the non-conducting solid sphere. This is the charge per unit volume into volume of the Gaussian volume inside the Gaussian surface is 4 by 3 pi small r cube. That is epsilon naught 4 pi r square E phi E equal to 4 pi r square E equal to Q by 4 pi r cube 4 by 3 by r cube 4 by 3 by r cube 4 by 3 pi small r cube. 4 by 3 pi cancelled out, r square cancelled out, r, which becomes E equal to 1 by 4 pi epsilon naught q small r divided by r cube. Q small r divided by r cube. Thank you.